like to talk. Thank you. One of the things I'd like to give a little insight into today is the mathematical basis for hearing. For example, if a musical tone, a pure musical tone, would consist of a pure oscillation in terms of the vibration of the air, it would be a pure oscillation. So, and if you superimpose upon that, suppose you sing a triad, ba, 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 ba. Those are three tones. Each has its own period of oscillation. So, and then another one, which is the top one, which is even faster. The higher it is, the faster thing. Anyway, so those three things, what you hear then is the sum of those things. So C plus G, let's say. What you hear is the waveform that, like it says, it's periodic still, but it's a mess. I don't know. I can't draw it. So this is periodic, but a mess, some sort of mess. Now, of course, if you hear the three tones together, most people, if they're not tone deaf anyway, can hear the three tones that make up that. So in other words, if this is the function, which is the sum of those three, some sort of a messy function, f of t, you're able to do Fourier analysis on it and break it up. You're able to take that f of t and somehow mentally express it as the sum of three pure oscillations. That's Fourier analysis. We've been doing it with an infinite series, but it's okay. It's still Fourier analysis if you do it with just three. So in other words, the f of t is going to be the sum of let's say sine, I don't know. It's going to be the sine of one frequency plus the sine of another frequency plus the sine of a third, maybe with coefficients here. So somehow, since you were born, you have been able to take the f of t and express it as the sum of the three sines, and hear, therefore, the three tones that make up the triad. Now, the question is, how did you do that Fourier analysis? In other words, does your brain have a little integrator in it which calculates the coefficients of those series, of that series? And of course the answer is no. It has to do something else. So one of the things I'd like to aim at in this lecture is just briefly explaining what in fact actually happens to do that. Now to do that we'll have to make, of course, some little detours as always. So I'd like to first, I'm going to, throughout the lecture, in fact, I gave you last time a couple of shortcuts for calculating Fourier series based on evenness and oddness, and also some expansion of the idea of Fourier series where we used a different, the thing didn't have to be periodic of period 2 pi, but it could have an arbitrary period 2L, and we could still get a Fourier expansion for it. Let me therefore begin by, just as a problem, another type of shortcut exercise to do a Fourier calculation, which we're going to need later in the period to explain the music problem. So let's suppose that we're starting with the function f of t, which looks like is a real square wave, and I'll make its period different from the one not 2 pi. But so suppose we had a function like this. So this is 1, and this is 1. So the height is 1, and this point is 1 as well. and then it's periodic ever after that. Tell you what, let's do like the electrical engineers do and put these vertical lines there, even though they don't exist. Okay, since the height is 1 and it goes over the period, the half period is 1, this really is a square wave. I mean, it's really a square, not what they usually call a square wave. So my question is, what's its Fourier series? Well, it's neither even nor odd. That's a little dismaying. That sounds like we're going to have to calculate ANs and BNs. So the shortcuts I gave you last time don't seem to be applicable. Now, of course, nor is the period 2 pi, but that shouldn't be too bad. In fact, we ought to look for an expansion in terms of things that look like sine of n. Well, what should it be? Since L is equal to 1, the half period is equal to 1. Remember, the period is 2L, not L. It's n pi over L, but if L is 1, we should be looking for an expansion in terms of functions that look like this. Now, since we've already done the work for the official square wave, which looks something like this, what you always try to do is reduce these things to problems that you've already solved. Now, this is a legitimate one, since I solved it in lecture for you, so we can consider it as something we know. So I observe that, since I'm very lazy, that if I lower this function by 1/2, it will become an odd function. Now it's an odd function. Okay, I just cut the work in half. So let's call this function, and let's call this, I don't know, S of t. The green one is the one we wanted to start with. So f of t is the green function. But I can improve things even a little more, because the function that we calculated in the lecture was a lot like this salmon function. That's why I called it S. But the difference is that the function we calculated was this one. First place, it went down further. It went not to -1/2, which is where that one goes, but it went down to -1, and then went up here to +1, and it went over to pi. So it came down again, but at the point pi, and here -pi went up again. Okay, let me remind you of what this one was. Suppose we call it, O doesn't look good. I don't know. How about G of U? Let's for a secret reason call the variable U this time, okay? So the previous knowledge that I'm relying on was that I derived the Fourier series for you by an orthodox calculation, and it's not too hard to do, because this is an odd function, and therefore you only have to calculate the BNs, and half of them turn out to be 0, although you don't know that in advance. But anyway, the answer was 4 over pi times the sum of just the odd ones, the sine of nu, and then you had to divide by n. So this was the expansion of g of this function g of u. The Fourier expansion of this function g, since it's an odd function, it only involves the sines. There's no funny stuff here because the period is now 2 pi. And this came from the first lecture on Fourier series, or from the book, wherever you want it. Or solutions to the notes. There are lots of sources for that. The solutions in the notes. Okay, now, that looks so much like the salmon function, I ought to be able to convert one into the other. Now, I'll do that by shrinking the axis, but since this can get rather confusing, what I'll do is overlay this, what I prefer to do is, I think u, okay, I'm keeping the thing the same, but I'm going to change the name of the variable to t in such a way that on the t-axis, this becomes the point 1. If I do that, then this function will turn exactly into that one, except it will go not from minus a half to a half, but it will go from -1 to 1, since I haven't done anything to the vertical axis. So how do I do that? What's the relation between u and t? Well, u is equal to pi times t, or the other way around. If you know that it's going to be approximately this, try one and then check that it works. When t is equal to 1, u is pi, which is what it's supposed to be. So this is the relation between the two. And therefore, without further ado, I can say that, let's write the relation between them. F of t is what I want. Well, what's f of t if I subtract 1/2 of that? So that's going to be equal to the salmon function plus 1/2, right? Or the salmon function is f of t lowered by 1/2. One thing the same as the other. And what's the relation between the salmon function and the orange function? Well, the salmon function is, let's convert, so s of t, it's more convenient since I wrote the formula for g of u. Let's start it from that end. If I start from g of u, what do I have to do to convert it into into the salmon function? Well, take 1/2 of it. So if I put them all together, the conclusion is that f of t is equal to 1/2 plus s of t, which is 1/2 of g of u, but u is pi t. So it's 4 over pi times the sum of the sine of n, and for u I will write pi t divided by n. And the sum is only, sorry, I forgot to say that the sum is only over the odd values of n, not all values of n. So the sum over n odd of that, and of course the 2 will cancel that. So here we have, in other words, just by this business of shrinking, or just stretching or shrinking the axis, lowering it, and squishing it that way a little bit, we get from this Fourier series, we get that one, just by this geometric procedure. I'd like you to be able to do that because it saves a lot of time. Okay, so let's put this answer up in. I'm going to need it in a minute, but I don't really want to recopy it. So let me handle it by erasing. So let's call that plus 2 over pi. And there's our formula for that green function that we wrote before. So I'll put that in green. So we'll have a color-coded lecture again. Now, what we're going to be doing ultimately to getting at the music problem that I posed at the beginning of the lecture is we want to solve, and this is what a study of Fourier series has been aiming at, to solve second-order linear differential equations with constant coefficients where the right-hand side was a more general function than the kind we've been handling. So now, in order to simplify, and we don't have a lot of time in the course, I'd have to take another day to make more complicated calculations, which I don't want to do since you won't learn a lot from them anyway. I think you'll find you've had enough calculation by the time Friday morning rolls around. So let's look at the undamped case, which is simpler, or undamped spring, or undamped anything, because it doesn't have that extra term, which requires extra calculations. So I'll follow the book now and some of the notes, and the visuals, and call the independent variable, the dependent variable, I'm going to call x now, and the independent variable is, as usual, will be time. So this is going to be, in general, f of t, and I'm going to use in my calculating example, this is the actual f of t I'm going to be using. But the general problem for a general f of t is to solve this, or at least to find a particular solution. That's what most of the work is, because we already know how from that to get the general solution by adding the solution to the reduced equation, the associated homogeneous equation. So all our work has been this past couple of weeks in how you find this particular solution. How do you find a particular solution? Now, the case in which we know what to do is, so we can find our particular solution. Let's call that x sub p. We could find x sub p if the right-hand side is cosine omega, well, in general, an exponential, but since we're not going to use complex exponentials today, all these things are real, and I'd like to keep them real. If it's either cosine omega t or sine omega t, or some multiple of that by linearity is just as good, we already know how to find the thing and to find the particular solution. So the procedure is use complex exponentials and that magic formula I gave you. But right now, to save a little time, since I already did that in the lecture on resonance, I solved it explicitly for that, and you had adequate practice, I think, in the problem sets. Let's simply write down the answer that comes out of that. The answer for the particular solution is cosine omega t or sine omega t. That's the top. And it's over a constant, and the constant is omega naught squared. That's the natural frequency which comes from the system, minus the imposed frequency, the driving frequency that it's being driven, that the system, the spring or whatever it is, undamped spring, is being driven with. Okay, you understand the notation. It's a little cosine this over that, or sine, depending on whether you started driving it with cosine or sine. So this is from the lecture, if you like, from the lecture on resonance. But again, it's, I hope by now, a familiar fact. Let me remind you what this had to do with resonance. The observation was that if omega, the driving frequency, is very close to the natural frequency, then this is close to that. The denominator is almost zero, and that makes the amplitude of the response very, very large. And that was the phenomenon of resonance. Okay, now what I'd like to do is apply those formulas to finding out what happens for a general ft, or particular this one. So in general, I'll keep using the notation f of t, even though I've sort of used it for that. But in general, what's the situation? If f of t is sine series, cosine series, all right, let's do everything. Suppose it's, in other words, the procedure is take your f of t, expand it in a Fourier series. Well, doesn't that assume it's periodic? Yes, sort of. So suppose it's Fourier series. I'll make a very general Fourier series. Write it this way. Cosine omega nt, and then the sine terms, sine omega nt, from 1 to infinity, where the omegas are, omega n is short for that, well, it's going to have the n in it, of course, but I want now to make the general period to be 2L, so it would be n pi over L. Of course, if L is equal to 1, then it's n pi, or if L equals pi, those are the two most popular cases by far, then it's simply n itself, the driving frequency. But this would be the general case, n pi over L if the period is, the period of f of t is 2L. So that's what the Fourier series looks like. Okay, then the particular solution will be what? Well, I got these formulas. In other words, what I'm using is superposition principle. If it's just this, then I know what the answer is for the particular solution, the response. So if you make a sum of these things, a sum of these inputs, you're going to get a sum of the responses by superposition. So let's write out the ones we're absolutely certain of. What's the response to here? Well, it's an cosine omega nt. The only thing is now it's divided by omega naught squared. This constant has changed. And the same thing here. Of course, by linearity, if this is multiplied by a, then the answer is multiplied by. The response is also multiplied by a. So the same thing happens here. Here it's bn over, again, over omega naught squared minus omega times the sine of omega t. So in other words, as soon as you have the Fourier expansion, the Fourier series for the input, you automatically get this, by just writing it down, the Fourier series for the response. That's the fundamental idea of Fourier series, at least applied in this context. They have many other contexts, approximations, so on and so forth, but that's the idea here. All right, what about that constant term? Well, this formula still works if omega equals 0. If omega equals 0, then this is the constant 1. The formula is still correct. Omega is 0 here. The only thing you have to remember is that the original thing is written in this form, so the response will be, what will it be? Well, it's 1 divided by omega naught squared, if omega, I'm in the case omega 0, is equal to 0. So it's a0 divided by 2 omega naught squared. And as you'll see, that looks just like the others. You're just taking omega and making it equal to 0. For that particular case. Sorry, this should be omega n. Omega n is all the way through here. All right, well, let's apply this to the function the green function. So what do we got? We have its Fourier series. So if the green function is, if the input, in other words, is this square wave, the green square wave, so in your notes, this guy, this particular f of t is the input, then and the equation is x double prime plus omega naught squared x equals f of t, then the response is, well, I can't draw you a picture of the response because I don't know what the Fourier series actually looks like, but let's at least write down what the Fourier series is. The Fourier series will be, well, what is it? It's 1/2, the constant out front is 1/2, except it's 1 over 2 omega naught squared. So I'm taking, this is my function, f of t. That's the general formula for how the input is related to the response, and I'm applying it to this particular function, f of t, and the answer is plus, well, my Fourier series involves only odd sums, only the summation over odd, and only of the signs. So it is going to be 2 over pi, So it's going to be 2 over pi out front. That constant will carry along by linearity. And I'm going to sum over odd and odd values only. The basic thing in the upstairs is going to be the sine of omega nt. But what is omega n? Well, omega n is n pi. So it's n pi t. And how about the bottom? The bottom is going to be omega naught squared minus omega n squared, and this is my omega n, minus n pi squared. What's that? Well, I don't know. All I could do would be to calculate it. You could put it on MATLAB and ask MATLAB to calculate and plot for you the first few terms and get some vague idea of what it looks like. But that's nice, but it's not what's interesting to do. What's interesting to do is to look at the size of the coefficients. And again, rather than do it in the abstract, let's take a specific value. Let's suppose that the natural frequency is of the system, in other words, the frequency at which that little spring wants to go vibrate back and forth, whatever you got vibrating. Let's suppose the natural frequency, that's omega naught, is 10. For the sake of definiteness, as they say. Okay, if that's 10, all I want to do is calculate in the crudest possible way what a few of these terms are. So the response is, let's see, we've got to give that a name. The response is xp of t. What's xp of t? I'm just going to calculate it very approximately. This means, throwing caution to the winds because I don't have a calculator with me, and I want you to look at this thing without a calculator. The first term is 1 over 200. Okay, that's the only term I can get exactly right. Or I could if I could calculate. I suppose it's 0.005, right? That's the constant term. Okay, so the next term, so let's see, 2 over pi is 2/3. I'll keep that in mind, right? 2 plus 2/3, 0.6, let's say. That's an indication of the accuracy with which these things are going to be performed. So I think in Texas for a long while, the legislature declared pi to be 3 anyway. So one of those states did it to save calculation time. I'm not kidding, by the way. The sine of, all right, so what's the first term? If n equals 1, I have the sine of pi t. That's the n equals 1 term. What's the denominator like? That's about 100 minus 9 squared. Let's say it's 91. Sine t over 91. What's the next term? Sine of 3 pi t. Remember, I'm only using the odd values of n because those are the only ones that entered into the Fourier expansion for this function, which is at the bottom of everything. All right, what's the sine 3 pi t? Well, now I've got 100 minus 3 pi, that's 9 squared, is 81. So that's, no, what am I doing? So we have 100 minus 3 times pi is 9 squared. Is a little more. Let's say 83 times 85. So that's 15. How about the next one? Well, it's sine 5 pi t. I think I'll stop here as soon as we do this one, because at this point it's clear what's happening. This is 100 squared minus, that's 15 squared is 225, so that's about 125 with a negative sign. So minus this divided by 125. And after this, they're going to get really quite small because the next one will be 7 pi squared, that's 400, and this is becoming negligible. So what's happening? So x, it's approximately, in other words, 0.005 plus the next coefficient is, let's see, 6/10 of 190, let's say 100th. Sine pi t. And what comes next? Well, it's now 1/20th. It's about a 20th. Let's call that 0.05. Sine 3 pi t. And plus and now so small, minus 0.01, let's say, times this last one, sine phi pi t. What you find, in other words, is that the frequencies which make up the response do not occur with the same amplitude. What happens is that this amplitude is roughly 5 times larger than any of the neighboring ones, and after that it's a lot larger than the ones that come later. In other words, the main frequency which occurs in the response is the frequency 3 pi. That's what's happened is, in other words, near resonance has occurred. So if omega is 10, very near resonance, that is, it's not too close, but it's not too far away either, occurs for the frequency 3 pi in the input. Now, where is the frequency 3 pi in the input? It isn't there. The input is just that green thing. Where in that is the frequency 3 pi? I can't answer that for you, but that's the function of Fourier series, to say that you can decompose that green function into a sum of frequencies, as it were, and the Fourier coefficients tell you how much frequency goes into each of those f of t's. Now, so f of t is decomposed into frequency by its sum of frequencies by the Fourier analysis, but the system isn't going to respond equally to all those frequencies. It's going to pick out and favor the one which is closest to its natural frequency. So what's happened, these frequencies, the frequencies in and their relative importance in f of t are hidden, as it were. They're hidden because we can't see them unless you do the Fourier analysis and look at the size of the coefficients. But the system can pick out. The system picks out and favors, picks out for resonance, or resonates with the frequencies closest to its natural frequency. Well, suppose the system had natural frequency not 10. This is a put-up job. Suppose it had natural frequency 5. Well, in that case, none of them are close to the hidden frequencies in f of t, and there would be no resonance. But because of the particular value I gave here, I gave the value 10, it's able to pick out 3, n equals 3, as the most important the corresponding 3 pi as the most important frequency in the input and respond to that. Okay, so this is the way we hear. You know, give or take a few thousand pages. So what does the ear do? How does the ear? So it's got that thing, messy curve, which I erased, which has a secret 3, which just had 3 hidden frequencies. Okay, from now on I hand wave, right? Like they do in other subjects. So we got our frequency. It's got a blah, that's one frequency. Blah, that's another. And blah. And you're hearing the ear. What goes in there is the sum of those 3. And the ear has to do something to say, out of all the frequencies in the world, I'm going to respond to that one, and that one, and send a signal to the brain, which the brain then will interpret as a beautiful triad. Okay, so what happens is that the ear, I don't talk physiology, and I never will again. I know nothing about it. But anyway, the ear, when you get far enough in there, the little 3 bones, bang, bang, bang. There's an eardrum, and then there's the part which has wax. And then there's the eardrum, which vibrates, at least if there's not too much wax in your ear. And then the vibrations go through 3 little bones, which send the vibrations to the inner ear, which nobody ever sees. And the inner ear then is filled with fluid, a thick fluid, and a membrane, and that the bones hit up against, the last bone hits up against the membrane vibrates, and that makes the fluid vibrate. Okay, good. So it's vibrating according to the function f of t. But what then? Well, that's the marvelous part. It's almost impossible to believe, but there's this sort of like a snail thing inside. It's the part, I forgot the name. It's something like cochlea. And it has these hairs. They're not hairs, really. They're just, I don't know what else to call them. They're not hairs. But they're things one cell long. You know, they stick up. And there are 20,000 of them. And they're of different lengths, and each one is tuned to a certain frequency. Each one has a certain natural frequency, and they're all different, and they're all graded, you know, just like a bunch of organ pipes. And when that complicated wave hits, each one resonates to a hidden frequency in the wave, which is closest to its natural frequency. Now, most of them won't be resonating at all. Only the ones close to the frequency, they'll resonate, and the nearby guys will resonate too because they'll be nearby, almost have the same natural frequency. And over here, there'll be a few which resonate to da, and finally over here, a few which go da. And each of those little hairs, little groups of hairs will send its signal to the auditory nerve somehow or other, which will then carry these three inputs to the brain, and the brain then will interpret that as you are hearing ba-da-da. So the Fourier analysis is done by resonance. You hear by resonance, because each of these things has a certain natural frequency, which is able then to pick out a resonant frequency if in the input. I'd like to finish our work on Fourier series. So for homework, I'm asking you to do something similar. Take an input, I give you a frequency here, a different omega naught, a different input, ask you by means of this Fourier analysis to find out which it will resonate, which of the hidden frequencies in the input the system will resonate to, just so that you can work it out yourself and do it. Now, I'd like to first try to match up what I just did by this formula with what's in your book, since your book handles the identical problem but a little differently, and it's essentially the same, but I think I'd better say something about it. So the book's method, and to the extent to which any of these problems are worked out in the notes do this too. Use substitution. Base uses differentiation of Fourier series, term by term. The work is almost exactly the same as here, and it has a slight advantage that it allows you, the book's method has a slight advantage that it allows you to forget this formula. You don't have to know this formula. It will come out in the wash. Now, for some of you, that may be of colossal importance, in which case, by all means, use the book's method, term by term. So it requires no knowledge of this formula, because after all, I based this solution, I simply wrote down the solution, and I based it on the fact that I was able to write down immediately the solution to this input as being that response, and for that I had to remember it or be willing to use complex exponentials quickly to remind myself. There's very, very little difference between the two. Even if you have to rederive that formula, the two take almost about the same length of time. But anyway, the idea is simply this. What the book, you assume in other words, you take your function f of t, you expand it in a Fourier series. Of course, which sines and cosines you use will depend upon what the period is. So you assume the solution of form. Well, if I, for example, carried it out in this particular case, I don't know if I'll do all the work, but it would be natural to assume a solution of the form, since the input looks like how? The input looks like the green guy. Assume a solution which looks the same. In other words, it'll have a constant term because the input does, but all the rest of the terms will be signs. So it'll be something like Cn times the sine of n pi t. The only question is, what are the Cn's? Well, I found them by one method up there, but the general method is just plug in, substitute into the ODE. Substitute into the ODE. You differentiate this twice to do it. So I'll do the double differentiation, and I'll stop. I won't stop the lecture there, but I will stop the calculation there because it has nothing new to offer. This is the way all the calculations in the books and the solutions in the notes are carried out, so I don't think I'll be in trouble. What is this? Well, this term vanishes. This term becomes what? If I differentiate this twice, I get summation. So this is 1 to infinity, because I don't know which of these are actually going to appear. Summation 1 to infinity, Cn times, well, if you differentiate the sine twice, you get negative sine, right? Do it once, you get cosine. Second time, you get negative sine. But each time, you'll get this extra factor n pi from the chain rule. And so the answer will be negative Cn times n pi squared times the sine of n pi t. And so the procedure is, very simply, you substitute x p prime double prime into the differential equation. In other words, if you do it, we'll multiply this by omega naught squared, and you add them. And then on the left-hand side, you're going to get a sum of terms sine n pi t times coefficients involving the Cn's. And on the right, so you're going to get a sum involving the Cn's and the sines n pi t. And on the right, you're going to get the Fourier series for f of t, which is exactly the same kind of expression. The only difference is now the signs have come with definite coefficients. And then you simply equate the coefficients on the left and the coefficients on the right and figure out what the Cn's are. So by equating coefficients, you get the Cn's. Would you like me to carry it out? Yeah, maybe okay, it'll take us out. I was going to do something else, but I wouldn't have time to do it anyway. So why don't I take 2 minutes to complete the calculation, just so you can see you get the same answer. All right, what do we get? If you add them up, you get C naught out front plus Cn is multiplied by what? Well, minus from the top, it's multiplied by omega naught squared. On the bottom, it's multiplied by n pi squared. Aha, where have I seen that combination? The sum is equal to, 1/2 plus, what is it, sum over n odd of n sine n pi t over n. So the conclusion is that, it should be C naught times omega naught squared. So what's the conclusion? That C0 is 1 over 2 omega naught squared, and that Cn, only for n odd, the others will be even, the others will be 0, the Cn is going to be equal to 2 over pi here. So it's going to be 2 pi, 2 over pi times 1 over n times 1 over omega naught squared minus n over pi squared. This is terrible. Which is the same answer we got before, I hope. Did I cover it up? Same answer. So that answer at the left-hand end of the board is the same one. I've calculated, in other words, what the C zeros are, and I got the same answer as before.